Good morning, class. Hopefully you're all in your PJs and ready to do some math today because I didn't want you to miss the opportunity to get some math lessons in. So right now I'm going to go over lesson 63 with you, and we're not going to do the warm-up or anything. We're just going to go right to the lesson, so it shouldn't take all that long to be able to get that done. Okay, so I'm kind of have to squeeze in here so I can get the paper so that you can see it and me too. Okay, so so far what we have learned is changing denominators so that denominators are equal so that we can go ahead and add or subtract them. Then we talked about adding and subtracting mixed numbers, and now we're going to put those two together. So when we have mixed numbers and we have different denominators, we have to change those denominators so that they are the same. For example, if I have 2 and 2/3, hopefully you can see all this, and I want to subtract 1 and 1/2 from that, then how am I going to do that? Well, the only way that I have to do that, since I have thirds and I have halves, is to change the denominators so that they are the same. So I'm going to go ahead, it's hard to write this way, and I am going to change 2/3 into 6 because 3 and 2 have a common denominator of 6. So to do that, I'm going to multiply the top by 2 halves. So I end up with 2 and 4/6. And I'm going to multiply this bottom one by 3/3. So that'll give me 1 and 3/6. Now I have a problem that I can actually do. So I have 2 and 4/6 minus 1 and 3/6. So if I subtract 1 from 2, that gives me 1. And if I take 4/6 minus 3/6, I end up with 1/6. So my answer then is 1 and 1/6. Okay, let's do one more together before I set you off on doing your own lessons there. The next one is 4 and 1/2 minus 2 and 2/3. Okay. This one is very similar to the other one, but you're going to find that there's a little bit of a twist. So again, we're going to need to change each of those into 6. So I'm going to do that by multiplying the top by 3/3, the bottom by 2 halves, and end up with 4 and 3/6. And then on the bottom, I'm going to end up with 2 and 4/6. Now, do you see a problem that we have here? We can't take 3/6 and subtract 4/6 from it. So what we're going to have to do is take this whole number 4, make it into 6, just like pies. We cut up that pie into 6. So now what we're going to end up with, we're going to take and we're going to borrow, we're going to make this a 3, we're going to add 6/6 to this side. Now we're going to have, our problem is going to be 3 and 9/6 minus 2 and 4/6. So what I end up here now is 1 and 5/6. So those are pretty much the two things that you're going to run into. The only additional thing you may have to do is either simplify or regroup down here. But pretty much that's going to be it. So happy lesson 63, and I'd like you to go ahead and do all of those problems. Thanks. Welcome back, class. Now this is lesson 64. Once you listen to this and the 63, then go ahead and do your lessons, and then we'll hopefully meet back on Thursday. All right, so now we're going to talk about circles and angles. A segment or an arc subtends an angle if basically it crosses the path of the endpoints of the angle. So we would say that arc AC subtends angle ABC because it crosses the path, or we would say the endpoints lie on the sides of the angle. It's easier to think of that if it crosses its path. We can also have a segment, like if I drew a line, do that. If I drew a line here from A to C, then I would say that segment also subtends the angle because it crosses the path of the endpoints. Okay. Inscribed angles are angles that are subtended angles because they have the circle crosses the path of the endpoints there. Okay. Tangents and chords also form subtended angles. So if I look down here, if I look at this tangent here, we kind of think of this point here and this point here as the arc subtending this area right here. Even though we don't have an endpoint out here that it crosses, it touches here and it touches here. So this angle that this is making here has this point and this point, so that this arc actually subtends angle DBC, okay, and it's subtended by DEB. Now this is significant because we can figure out the measures of these angles by knowing what part of the arc subtends it, okay. We already know that in an inscribed angle, angle B here is equal to 1/2 of arc AC. And the reason for that is because of this theorem. It's actually 64-1. And which that 64-1 has to do with tangents, but it's the same principle. So we can use this same idea of the inscribed angle to figure out what angles that are formed by tangents in circles and chords make. Okay, so if I want to figure out what angle DBC is, what the measure of that is, then I just need to know what the arc length of angle DEB is, because this measure of angle DBC is going to be 1/2 of the arc length of DEB. Likewise, if I want to know the angle measure of DBA, it's going to be 1/2 the arc measure of DB here. Okay, so it's very helpful to help us figure these things out. Okay, let's say that I know the measure of DEB here is 196 degrees. Well, how would I determine then what is the measure of angle DBC? Well, since I just told you that it's 1/2 of this arc length, then I could use that information to be able to determine that, right? So if this is 196, then that must mean this is 98. I know it's not drawing a scale. Also, another thing that we can learn here is to be able to figure out, oh, well, let's do this one. Let's look at this one. What if I wanted to know what this one was here? Well, let's pretend that one wasn't there, and let's say this was, I don't know, let's say that this was 84 degrees, okay? Well, if I know this arc length here is 84 degrees, then I would know this angle is 1/2 of that, which would be 42 degrees. So you get the idea. Okay, another thing that we can figure out from this, we can get from this same idea, is that what happens when we have a circle and we have chords that cross inside of here. Okay, so we have intersecting chords. If we have intersecting chords there, I can figure out the angle measure of these things as well. And that's what Theorem 64-2 says. It says the measure of an angle formed by two chords intersecting in a circle is equal to 1/2 the sum of the intersected arcs. Okay, so let's say I have 1 and I have 2. Okay, well, let's name these two. So A and B and C and D. So what I can figure out then, oh, here we go again, sorry, is that the measure of angle 1 here is going to be the measure of AB plus the measure of DC. If I put those together and take 1/2 of that, I will know what the measure of angle 1 is. And also it's opposite because they're vertical angles, right? The measure of angle 2 then is going to be 1/2 of the sum of arc BC plus arc AD. It is very useful information for determining these angle measures in there. Okay, so let's go ahead and do a problem, and then I'll set you off to do your lessons. So let's say I have a circle here, and I have a chord here, and I know that this is 68 degrees, and I know that this is 172 degrees. And I would like to know what is the measure of x. Okay, well, I just told you that I can determine the measure of x if I know the measure of the arcs that both intersect. Okay, so I need to know this arc plus this arc, and I need 1/2 of that. So I'm going to take 172, I'm going to add to it 68 degrees. Whoops. 240, right? I'm going to get 240. If I divide that by 2, that will give me 120 degrees is going to be equal to x. Okay? So hopefully that gives you a good idea of what we're doing here. Go ahead and do your lesson problems, and I'll send in your email what you're supposed to do. And if you have any questions, make sure that you ask me on Thursday or send me an email back, and I'd be happy to answer them. Have a good day. Hi, class. Didn't want you to miss geometry just because we're off school. So I'm going to go over lesson 63 and 64 with you. This is going to be 63, and then I'll send another video for 64. All right, so we're going to be discussing vectors. If you ever watched the movie Despicable Me, you know all about vector because he was doing crimes with both direction and magnitude. And that's what a vector is. It's something that has both direction and magnitude. If we have something that has only magnitude, we call that a scalar quantity. And if we have something that has both direction and magnitude, we call that a vector quantity. Those are things like acceleration and velocity, whereas speed is a scalar quantity because it's only a magnitude. We just talk about how fast something's going. When we give it a direction, when we say something's traveling north at 75 miles per hour, that's actually a vector. It's a vector quantity because it has both of those components. Magnitude is the number, or how large or small something is, and then the direction is often given by a degree from the positive x direction. So we would start here, and as we increase, we can give that an actual degree. So if we say something's traveling at 40 degrees, with a magnitude of 5, then we can start from the positive x direction, go up 40 degrees, and know that it's headed in that direction with a magnitude of whatever we give it. Okay, there's two parts to a vector. There's the initial part, which is where it starts from, and then there's the terminal part of the vector, and that's where it ends. Pretty easy. Start, finish, initial, terminal. We can name it in a couple different ways. Oftentimes we do a letter. We might say A, we can just say vector A, or we can put a line with a little swoopy on it, like a one-sided arrow there. So that would be how we would name that. I've named this vector V. And so this would be its initial point, and this would be its terminal point, okay, or the end point. Okay, when we add vectors together, we think about placing them. If I take my initial point and my end point, and I take the next vector and put its initial point at that end point, then we think about what direction we would go. And if you go back and look at the warm-up, you'll find that that's what they had you do. So when we add vectors together, that's what we're going to be looking at. And if we visualize it that way, it helps us to be able to do that. Also, when we're thinking about just the magnitude of a vector, we use absolute value signs. So if I want to know what is the magnitude of vector A, I would put the absolute value signs around it, and so that indicates that I'm only looking for the magnitude. I'm not looking for the direction. Okay. Also, if we place a vector at the origin, sometimes that makes it's easier to be able to calculate too, because we can put these on a coordinate plane. And when we do, and we want to figure out what the magnitude and direction of that is, what the components are, we would talk about, it's easier to put it at the origin. Okay, but first of all, let's just think about if I want to figure out what the magnitude of a vector is. Okay, so let's say that for our purposes here, that the initial point is at 0, 0, and the terminal point up here is at 3, 5. Well, I can kind of think about that like a triangle. So if I form this, if I make this into something like a triangle, then what I end up with is I have, since I've gone over 3, I have 3 here. Since I've gone up 5, I have 5 here. So I can figure that out just by using the Pythagorean theorem because I've made a right triangle here. So in order to figure out the distance of this vector, I would take 5 squared plus 3 squared, and then I would go ahead and take the square root of that, and that would give me my vector, the magnitude of vector V. My little makeshift idea is falling down. All right, so I would have the square root of 25 plus 9, and then that would be the square root of 34. And that's, and then since that's 2 times 17, I just have the square root of 34. So that would be my magnitude of that vector. So that's pretty much how you're going to do that. And if you get pretty familiar with that, we also do that in physics, so you get real good at doing vectors. Okay, now I also said that we can put them on a coordinate plane, kind of like I did here. But if you put them on a coordinate plane, then we give them components. And the way we do that is just the way I did here, only instead of using parentheses like I do coordinates, I'm going to use these little things called little brackety things there. Okay, so if I have, let's say I have a coordinate plane here. Well, it's kind of hard to do here, drawbacks of this type of thing. So if I had, let's say I have this going, this is my initial point, and I have this going up here as my terminal point. Okay, if that's the case, you know, you might not even be able to see that, can you? Okay, if that's the case, then I'm going to measure, I'm going to go ahead and count my horizontal first, my horizontal direction first. So here this would, from the initial point, I would move 1, 2, 3 spaces horizontal in the negative direction. So my first component is going to be a -3. Then I went up 1, 2, 3 in a positive direction, so that's going to also be a 3. So this vector component is -3, 3. Well, why do we want to write them in components? Well, it's helpful to write them in components because that helps us to very easily add vectors together. So, and they don't have to be end to end. So if I had another vector, let's say down here, okay, and I wanted to add this vector, that vector to it, and I wanted to add those two vectors together, well, I'm going to have to figure out what the components for this one is. I know it's hard to see there, but I started here, and then the change in position, I moved 1, 2, 3 spaces to the right, and then I went up 1. So my components for the first one is -3, 3. My components for the second one is 3, 1. All I have to do is just add those together. If I want to add these, I end up with 0, 4. So my overall change in my vectors when I put those together, so imagine that I stuck this vector at the initial point, at the terminal point here, and I went ahead and I went like this, right? Then my overall vector change would have been 0, 4. It would have been straight up. So it's really just the same as if I started off at one point and I walked 3 spaces to the left, and then I walked 3 spaces up. Then I walked 3 spaces to the right and 1 space up. Then from my original starting point, I actually didn't go left or right at all. I walked 4 spaces up. So that's how that works, to add vectors. We can also add, if we know that vectors are all the same. So let's say we have 4 vectors and their components are, let's say, 2, 4. Okay, well, I can multiply that like this, and I just multiply each component. So adding all those together would be 8, 16 then. Okay, so depending on, you know, like if you have them all the same, you can multiply however many you have there. Let's see. What else do we need to say here? You can add, sometimes vectors are going in the opposite directions, and you'll find that they cancel each other out. So what if we have the case here where we have, let's see if I can move this over. So what if we have the case where we have a vector doing this from here to here, and then we have another vector doing the very same thing. Okay, well, let's assume that this was 4, 0, and let's assume that this one, whoops, I can make that one go the other way, would be -4, 0. If I added those together, I get 0, 0. So my overall change was that I didn't move. And this is why direction is important when we're talking about vector quantities. Because if we were talking about actual velocity here, velocity, if I went and I started at a position and I went to the right, and then I turned around and went back to the beginning, my velocity actually is 0, whereas my speed will be however fast I was going when I went there, when I did that. So that's why direction makes a difference. I saw just something. So, that concludes vectors. Go ahead and do the problems in 63. I'm not sure whether I'm going to have you do even or odd, so I'll put that in the notes when I look at the book, and then I'll send you a video for 64. Hello again, class. We're going to talk about lesson 64 now. All right, so remember that we're going to do quadrilaterals here. So remember that a quadrilateral is a polygon that has 4 sides. So we have all different kinds of quadrilaterals that we can talk about. But first, we're going to name these categories. Okay, the 3 major ones are trapezium, which means that they have no sides parallel. It's just 4 sides that encloses the figure. So it's just a 4-sided polygon. And then the trapezoid, which is a quadrilateral, meaning it has 4 sides that has 1 parallel side. So as you can see here, we have the top and the bottom are parallel, the other 2 are not. Then we have the parallelogram that has 2 pairs of parallel sides. So this one, we have the sides and then the top and the bottom are parallel. Then from that, we have special kinds of parallelograms. So a rhombus is a parallelogram that has all equal sides in it. I don't think I drew that. Imagine something like a kite figure. Only they have to have all equal sides. Then we have a rectangle is also a special type of parallelogram, and a rectangle has all right angles. You know that. Then we have a square. A square is both a special type of parallelogram because it has both equal sides and right angles, but it's also a special type of rectangle as well because it has right angles, but it has all equal sides. Okay, so square is kind of special there. A square is a special kind of rectangle. A rectangle is a special kind of parallelogram. Parallelogram is a special kind of quadrilateral, and a quadrilateral is a special kind of polygon. Okay, so a couple little questions. So let's think about some things like, is it true or false? All parallelograms are rhombuses. Well, that would be false because we can have parallelogram that's a rhombus, a rectangle, or a square. So they can't all be rhombuses. How about all squares are rectangles? Well, since a square is a special kind of rectangle, then that would be true. All squares are rectangles. Okay. We have such jokesters here. All right, so let's think about what is the difference between a trapezoid and a parallelogram. Well, it would be in the number of parallel sides it has. So a trapezoid would have 1 pair of parallel sides, and a parallelogram would have 2 pairs of parallel sides. All right, so go ahead and do the practice, or not the practice, but do the lesson practice for lesson 64. I'm only going to have you do one or the other. I'll include that in the notes because I need to look and see whether you need to do odd or even. But hope you're enjoying your day off, and hope math makes it even more enjoyable.